All right, so we're gonna finish up plan today. We might finish lecture a little bit early. We end with a whole bunch of practice. But we're gonna plan on finishing up the chapter on alkenes today, and then we'll start talking about alkynes, which is triple bonds, but really similar because it's still carbon-carbon pi bonds. So they have a lot of similarities. So we'll start talking about those on Thursday. So let's quick quiz question, and then we'll go through the quiz problems. Which mechanisms can rearrange and how can we distinguish them from others? There are a few exceptions, but for the most part, the only time you really need to be paying attention to rearrangement is if you get a carbocation intermediate. Right, so all of those reactions that don't rearrange, it's because you're making some intermediate that's not stable, but it's also not fully a carbocation. It has that empty p orbital that can rearrange. Right, so when we have things that are acid catalyzed reactions, the first step is break the pi bond and make a carbocation. Those are always going to rearrange or be at risk for rearranging. But the oxymercuration, demercuration, the hydroboration, hydrogenation, halogenation, all those other ones that go through other intermediates are not going to rearrange. So really, the rearranging only happens with the simplest reactions. Yes. And then, Taylor, you specifically wanted to look at the ones where we had a different nucleophile for the oxymercuration, right? How can you go through any of these? Actually, especially considering this one is a rearrangement one.
Yeah, that's like I was going through it and I was looking at my notes and just trying to figure out which ones rearrange. But then there's always the case of ones that don't rearrange because already more sense since we did.
Right.
So I was.
So if it's not a carbocation intermediate, you don't need to worry about rearranging. At this point, we'll add a few other cases as we go on. But for the most part, that's what we're looking at, is that carbocation. So for this one, our first intermediate, well, we could write it as, we have two possibilities, actually. We could put the positive charge there and the hydrogen here, or we could put positive charge here if we had the hydrogen to the other side. This one can't rearrange.
Right.
This one can, which means all other things being considered, this is the more stable intermediate because it can rearrange. We'll get some amount of the product that comes here, but are more likely are thermodynamically favored product. If we give everything enough chance to settle into its most stable state, is going to be the one that where we go through this intermediate, it rearranges by dragging hydrogen across. And then we get a planar methyl on the tertiary carbocation. And then we're going to add the OH there. So this is definitely a mechanism that's going to give us a mess of products. Because not only do we have two different carbons where we can put the positive charge, but then one of those can go through rearrangement. So it's going to be a bunch of different stuff. They're all going to look like no pi bond and we added in. on these ones, where we're changing up the nucleophile, the main thing to be looking at is, it's just instead of having water come in and donate its lone pairs, we're gonna wind up with we're gonna make it an intermediate that looks like this. And then if it was water, we'd have H2O coming in here. And attaching to one of these, breaking that open, doing a ring opening reaction. The only difference with number 3 and number 7 from the quiz is it's not water that's our nucleophile. It's still gonna be a lone pair comes in and attaches though. So in this case, it's an ethyl group attached to a nitrogen.
I was wondering the product with these ones, is it just the nitrogen or is it the nitrogen still with ethyl attached?
The ethyl will stay attached to the nitrogen.
Okay.
So just like with water, we have to then do a proton transfer to kick off the extra hydrogen so we don't get an oxygen with free bonds. We'll do something similar here, but it's gonna be the proton that gets kicked off. We're gonna lose one of these hydrogens, not the ethyl group.
Yep.
So our final product here is gonna look like. We're gonna have the methyl up and then the nitrogen, hydrogen, ethyl down. And on this side, we're gonna have a mixture of methyl up and methyl down. So this is also gonna be a one that we're gonna get 4 different stereoisomers. So we're gonna get the one where both methyls are up and the nitrogen's down on this, on the far right. We're gonna get this methyl down, the rest of this looks the same. We're gonna get the one with both methyls down and the nitrogen up.
Don't draw them all out, right?
I mean, this is definitely one where we can't say we're favoring a specific stereoisomer. So it would not be a bad idea to draw them all out. Which I'm trying to think of if there's a good shorthand way that you could show it. So sometimes what you see is, even if it's a carbon that has a stereoisomer, they'll draw it without any stereochemistry shown. And then just say all 4 stereoisomers.
It's because of the sterics that it's favored to go on the right.
No, I'm just trying to keep track so I don't accidentally draw a different stereoisomer because the sterics should be identical. Both of those carbons are identical with the nitrogen could attach to, right? But if I attach to that one, instead I just get a different stereoisomer. So in the interest of being consistent, I'll just pick one and put it there and then just show all the stereoisomers from that point of view. The other thing you can do is you can draw 2 of the diastereomers, because there's, so there, if we draw this one, where the 2 methyls are cis relative to each other. Then the nitrogen's down. You do this one plus En, where we flip both of those, right? So where both the methyls are down and the nitrogen's up. And then we can draw the one of the stereoisomers where the methyls are trans relative to each other. And say plus En. So then you get away with only drawing two of them then, so that shows that you understand this. These are not enantiomers, right? Because we only flipped one of the stereocenters, so they're that other term, diastereomer. That would probably be the most comprehensive way to do it, but still save some time. But you're showing me you understand what the four isomers are.
Did we both get the last one? We did them separately, so I don't know which one.
I actually didn't look at your answers yet.
Okay.
I was just going fast and made sure I checked your questions first.
Yeah.
You mean on this one?
Yeah. Because that was the one where we like showed all the steps too.
Yes, we'll go through the mechanism for that one. Let's do the other.
Okay.
One with the other nucleophile here, because this one will be quicker because there's less stereochemistry in it. So in this case, we're going to put the mercury goes right there. We're going to add. So our intermediate looks like plus the other stereoisomer. Then we have the ETOH comes in. Oxygen is going to attach to the more substituting to the Markovnikov. So we're putting an OH. Our final result is we're going to put an OH right there, and we're going to get both stereoisomers. Sorry, we're going to put an ETOH. All right, so our final product is going to look like and actually, as long as if I want to be consistent with what I have on the board, the intermediate that I drew would give this stereoisomer. This one we have to worry about rearrangement. This one we have to worry about rearrangement. This one we have to worry about rearrangement.
Okay.
Those are all of our acid catalyzed ones. Our acid catalyzed addition goes through that carbocation intermediate.
The acid otherwise
Correct. So for this one, what's our first intermediate going to look like?
no high bond, but basically the same thing with
Is it going to rearrange?
yes.
Yeah, we're going to drag a methyl over. If there's a hydrogen to move over, the hydrogen will move over faster, it's smaller, easier. But if there's no hydrogen, a methyl is still small enough to be rearranged. So then our second intermediate looks like that.
It's the acid otherwise raise more for you.
And the hydrobromation. Anything where you have an alkene with acid, you should be thinking about rearrangement, because the first thing that's going to happen is you're going to do this. You're going to make a carbocation. If you,
Sorry.
I was just saying, if all you missed was the rearrangement, then that's still, I try not to break it down past a quarter of a point, but that's like, you got 3/4 of the point, that you were most of the way there, you missed the small.
The ring with the HPR though, that one's not gonna break if it's.
Correct.
Right?
And it's already.
Yeah.
It's already a tertiary carbocation, so. So we want to think about it and rule out rearrangements in that case. But as soon as you see that your first step is, oh, it's already tertiary carbocation, move it on. All right, other than the mechanism one, any other questions on these? Okay. Let's go through that mechanism. And then let me just. That is certainly helpful.
And I had 2 references in my notes, which was nice because I felt like both of them got funky along the way, so it's good to have 2 to go to, because then I piece it.
So this is the weird one that's gonna have all the repetitive steps, right? There's 3 different places where the same thing happens 3 times in a row. The first step is you bring your boron over, and it could be helpful to draw out your borane. So I bond is going to come in here, and one of your hydrides comes and attaches to the more substituted carbon. Right, so it's just because of the sterics. The boron goes and attaches to the less substituted carbon, so the hydride, which is the hydrogen that brings its electrons over, attaches to the more substituted carbon. And we're going to do that 3 times. So then we're going to get a boron that's attached to the less substituted carbon. Then we have 1, 2, 3, 4, 4. One, 2, 3, 4. 1, 2, 3, 4. This would be where it might be convenient to redefine them as R groups, so you don't keep redrawing that over and over again. Which would be fine, so you could just say R equals. And I would draw it like this once to make sure that you were on the right track, and then just say, equals B R R R, and say R equals.
I didn't define it, but I did start using R after drawing out.
So just like with any math problem, if you're gonna start using the variable, you gotta define what that variable is. Now, but again, once we have that understanding. That'd be like a, -1 out of 10, if you got the rest of the thing right. So. That gets us. That's the end of step 1.
Yes.
Step 2 is when we start making that really nasty peroxide ion. So sometimes it can be helpful to just sort of have in parallel or up off to the side. The part where, okay, HOOH hydroxide. It's gonna grab that to make. Ooh. Writing peroxides out like that always makes me want to pronounce it phonetically. Like Ruhr. So then the next step is just going to be one of those oxygens comes in here and attaches. So we get an intermediate that looks like this. Your hydroxide leaves. And your R group just moves over to the oxygen and it brings the electrons with it. Right? And it all comes back to electronegativity, right? Carbon can do this. The reason that the boron is so critical in this reaction, one, it's stable while having an empty p orbital. So that allows it to be stable with 3 bonds, but also stable with 4 bonds. But the other reason is because it's less electronegative than hydrogen and less electronegative than carbon. That allows things like this to happen, where the hydrogen gets to pull the electrons with it when it's over. Or in this case, the carbon moves over to the oxygen and gets to bring its electrons over. Normally, we don't see that. Normally, we don't see carbon pulling the electrons with itself when it moves. So we're going to do that 2 more times. So then we get we've inserted an oxygen between the boron and our R group in all 3 cases. So then now our last tricky step is we're going to do almost the same thing we just did, except with the hydroxide. And instead of doing a step where the R moves over to the oxygen, we're just going to have this as a leaving group. So it makes an intermediate that's going to look like OR, OR, OH, and another OR. This now has a negative charge because it's got 4 bonds. Which, if I was being really careful, this one should have had a negative charge on the boron too. And then that gives us a good leaving group. So after thinking about it over the weekend, all these repetitive steps, I'm okay with us when we draw this mechanism out. We don't have to draw the intermediate that still has 2 hydrogens and 1 R group. We just write the ×3.
2 hydrogen and 1 carbon.
So one of the reasons why we got hung up on, well, how many arrows are we drawing and when, is because the mechanism from the book said shows all the way out for the first time, and then it says that happens 2 more times. I'm fine with us showing step once and saying ×3,
Okay,
and going straight from pH3 to BR3
right.
without drawing that first step in the process. Because then we can just write ×3 anytime without that repetitive step happening. So then we're gonna wind up with BOH3. And really, it doesn't really matter for this class. We can leave it there. Really, what will happen is you'll get BOH4, which will rearrange itself to make, which is called tetraboric. We'll get, which shows up all the time in, you can actually buy that at a hardware store. I'm trying to think what it's used for right now, but it's actually, boric acid and sodium tetraborate are the most common ways you can get like a green flame, doing a flame test. I think it's a cleaning product. I think it's good for scrubbing things, if I'm remembering correctly. Either way, we're gonna get this.
Is it like hot?
No, I'm totally blanking right now, but I know you can buy it at the DIY store. And I've done it before. When you go into the DIY store, it's all the way back on the right hand side, which I think is cleaning products.
And then you just throw it on a fire.
And then you can throw it in the fire. I think it's Comet. I think Comet is sodium tetraborate. For,
Oh, like a powder.
yeah, it's a cleansing powder for dishwashing and cleaning stuff.
Cool.
Along with that, we're gonna get 3 of our ROH, or they're still deprotonated at this point, but 1, 2, 3, 4, is that. Putting the OH is gonna be on the less substituted carbon. And then if we just have something that has some hydrogens around, we just do a quick proton transfer. Our final product. Just like that, we'll get 3 of them. Will be, if we're actually going to stay balanced this whole way through, we probably should put a 3 there as well.
I got lost for this the very end. So the one with the VOH3, the like actual green with it on the, where did the extra that over? Oh wait, that's enough.
That's an O. So 1, 2, 3, 4 is still,
That's the same.
it's still methyl butane. We just put an O on carbon 1.
Okay.
So how'd you do?
I got it. I just drew it separate. I did like instead of a down, I went
Yeah.
another one. Same.
That's fine. I was just trying to run into this.
I forgot R, but I on the iPad, so I just like paste.
That's fine. Yeah. So it's a lot. It takes some practice, takes some getting used to, but that's what we're here for. And that in particular is one of the trickier ones because of all the ×3 and because it's involving boron and it goes around slower normal patterns. So that is one of the trickier ones that you'll see this for.
I mean, it's a long one for sure, but I feel like I like it better than the triple cyclic connection thingy. I don't put it out.
Well, that's Too bad, because we're gonna do more of that today.
Okay.
In fact, on the very next slide. So it's actually a different, it's a little bit different in that this is a functional group called an epoxide. An epoxide, it's a, you can call it a cyclic ether, because remember, an ether is just an oxygen in between two carbon chains, right? So a cyclic ether just means you've got a cyclo group where you've got an oxygen involved. If it's a cyclic ether that only has 3 sides to it, it's called an epoxide. It's far from the only common cyclic ether, because if you've taken your cell bio,
And you said the secret.
so
The big set.
an ether,
Oh,
all right, so here's an ether, just an example. You've got carbon, oxygen in between, right? If you make it a cyclic ether, just meaning it's a cyclo where one of the elements of that ring is an oxygen, it's a cyclic ether. Most common place you see this is anybody know what that molecule is? I'm actually not sure if I got all the stereochemistry right, but it's close. It's got a lot of alcohol. If you look at the formula, it's C6H12O6.
oh. It's sugar?
It's glucose. Basically, it actually might be galactose because it's what makes the difference between a lot of simple sugars. It's just what the stereochemistry is on these OHs. Are they up or down? But it's a cyclic ether when it's in its ring form.
So second ether is like probably an oxygen in the ring.
Exactly. So like a more simple cyclic ether would just be, it's an ether, it's a ring, but it's also a ring where one of the carbons is an oxygen. Right, so an epoxide is just a special case of this. Specifically, an epoxide is a 3-sided cyclic ether. Pretty much all sugars have a cycle structure, I think a ring form that is a cyclic ether. So like ribose and fructose are both 5-sided. In the case of fructose, it looks like this.
What about to break down to rings?
Basically, it's constantly interconverting between the ring form and the chain form, because as soon as you put this into an acidic environment, what happens, it's going to be so similar to what we're going to see here in a second, but basically the cyclic group will break apart and you'll wind up turning this into an open chain form that'll look something like CH2OH. And then you get a whole bunch of CHOH molecules down towards the bottom. But basically you turn this cyclic ether oxygen gets turned into a carbonyl. But it can kind of constantly be going back and forth between that. So there's really no difference. Some specific microbes, I want to say, favor one form of it over another. But if you go, the other term for glucose that is specifically one stereoisomer of glucose is called dextrose for right-handed. So there are like other forms of it, and there are some cases where dextrose gets used preferentially in the cell, but all of your glucose is constantly being converted back and forth between the two forms. more pressing question from a nutrition standpoint is there any difference between fructose and glucose? Because they're both C6H12O6. One of the most common enzymes in the human body. It's called fructoglucoisomerase. Its whole job is it converts glucose to fructose and fructose to glucose. Because we eat fructose, but our body uses glucose. Plants synthesize their sugars when they make fruit as fructose because it tastes sweeter.
Okay.
So the plants turn it into fructose because that attracts people into eating it more, and it's a stable way to store its energy. And then in eating fruit, we spread the fruit seeds more.
Right.
So that's advantageous to the plant. We choose the fruits that we eat based on the ones that taste best, which means more fructose and less glucose. But then our body turns around and takes that fructose, turns it to glucose because that's how our body actually needs it. So, long story short, there's no difference between fructose.
But if you eat fructose, you might burn more calories if you have to turn it.
Except it doesn't cost any energy or ATP to do that. What you could make the argument for is that you have to use less sugar to get the same level of sweetness if you're using fructose. So you could actually eat fewer calories that way. The problem with it is that fructose does affect metabolic pathways and signaling, basically insulin resistance, differently than just eating glucose. So there is a long-term effect of eating more fructose than glucose that has to do with your chances of developing type 2 diabetes.
Got it.
But that's all still not fully understood anyway. We're still trying to figure out what that all does. So basically, don't eat too much fructose or glucose, and you should be fine. But there's no point. While we're on the subject, the naturalistic fallacy really bothers me, which is just basically the idea that if it's natural, it must be healthier for you. Because people will tell you, you see it all the time, people say, oh, eliminate high fructose corn syrup, use agave nectar instead. Agave nectar, so high fructose corn syrup is like 55% fructose to 45% glucose. Agave nectar is like 90% fructose.
I like the sugars in coffee. We have some at home. And
Yeah.
I was putting it on my Rice Krispies. So like it's so yummy.
It's really good.
That's a lot of grams of sugar in 1 tablespoon.
Yeah. It's no different from an energy standpoint than just using high fructose corn syrup.
Right.
It is natural, so people like it. It does taste a little bit different.
Yeah.
It makes for a really good margarita, but from a health standpoint, you shouldn't know that.
I don't.
Yeah. All right. Anyway, natural does not equal good. Artificial does not equal bad. Was the
Yes.
where I was going with that. Let's talk about epoxides. So we can make epoxides from alkenes. This is our epoxide. This is our three-sided ring, three-sided cyclic ether. And as you might guess, they're not terribly stable. The mechanism for making this is just is one step, but it has 4 arrows. So it's a little bit tricky, and it makes what's called it uses what's called a peroxy acid. So remember, from hydrogen peroxide, peroxide just means you've got an oxygen with 2 oxygens with a single bond between them. Super unstable, prone to breaking down when you shine light on them. Makes free radicals bad for you.
That's peroxide.
So any peroxide element, the simplest peroxide is hydrogen peroxide. It just looks like this. Oops, that's a hydrogen. So H2O2 is hydrogen peroxide, but any peroxide is going to look something like this. You could have like with an R group on each side, you can have a R on one side and hydrogen on the other. But it's really this piece is what makes it a peroxide. So a peroxy acid is just a regular acid, carboxylic acid, except it's instead of being. So normally we would think of a carboxylic acid with this form, right? CO2H. In the case of acetic acid, it would just be CH3CO2H. If it's peroxy acid, you get there's 3 oxygens in here.
Difference is that there's.
Right. So peroxy acetic acid would be CH3CO3H. Or if we're drawing out the structure, it's going to look like this.
It's which one? It's some colors.
Yes, so it'll look like that.
But there's more than just this one, which I mean. Oh, that.
That's your peroxide bond. Is this one right here. So what this does is basically these peroxy acids are not super stable because you have this oxygen-oxygen single bond. They're also really prone to rearranging themselves. You basically just shuttle the hydrogen from one oxygen to a different oxygen and kick off that extra oxygen. So these are really strong oxidizing agents. They're not stable. They oxidize pretty much whatever you put them with, because if you kick off that extra oxygen, you make something that's a lot more stable. So going from peroxyacetic acid to acetic acid is way downhill in energy. So we wind up with this intermediate, or this mechanism step that basically looks like you can. I'm going to redraw it without all the arrows. Basically, you can kind of see that there's a pentagon formed by the oxygens, the hydrogen, and that carbonyl carbon. It's not a full cyclo group because there's no bond there. But you can kind of see that everything aligns so that this hydrogen can be kind of close to that oxygen. And so that all that's going to happen is this oxygen grabs the hydrogen.
Okay.
And it's showing it as being ion grabbing it, but it doesn't really matter. You can show it as being a lone pair either way. But then that means this pair of electrons is then free to go attack something else. Right, and the lone pair from the oxygen right here, or you can think of it as the bond. I always think of it as the lone pairs moving, but it doesn't really matter because all electrons are identical. So the net result of that is that this oxygen right here is now basically free to go do its own thing. And so what happens is that if you have a pi bond, carbon-carbon pi bond nearby, these electrons go to one side, pi electrons go towards the oxygen. So that's what this transition state is trying to show. got a whole bunch of bonds breaking and forming at the same time.
Put brackets around something that makes resistance.
Yeah, most, either you want to label it that way, or you should use that double daggers technically.
And the dotted lines.
Dotted lines represent either bonds breaking or bonds forming.
Okay.
So if we wanted to keep track of that here in this transition state, we can color code it and draw the bonds breaking in red. That bond is breaking. That bond is breaking. That bond is breaking. That bond is forming. That bond is forming. There's one more bond breaking. That bond, that double bond is breaking. This double bond is forming. And this oxygen hydrogen bond is forming. We drew 4 arrows right here, which means 4 pairs of electrons moving, which means 4 bonds breaking and 4 bonds forming. And the result of that big mess is an epoxide.
I still want to stay as the.
That's exactly where we're going. So epoxides, they're stable. Yeah, it's a strained ring structure. Yeah. But it's at least nothing's charged. With our oxymercuration step and our bromonium ion, both of those were ions. And so those really weren't going to be stable enough to stay that way. This one, at least everything's neutral. And if you want to get an idea for how long it can last, that's actually what epoxy is made of. Epoxy, the glue, gets its name because have you ever used epoxy before?
Yes.
It comes in 2 tubes, right? You've got to mix them.
Yeah.
One of those tubes is an epoxide, and the other one will help it go through a ring opening reaction, which is what we're going to see on the next slide.
They use it in dental.
Yeah, you can use epoxies get used in dental all the time, especially photo curing epoxies.
With the light.
With the light. Fun fact: the guy who invented that for dental use, or he didn't invent it, but he first brought it to dental. Was at University of Colorado. When I was there, he was. When I was there, he was one of the advisors. He was one of the faculty. It is. He was in my department. Chris Bowman, I think his name was. Maybe it was Steve George. I can't remember which one did which. But anyway, cool stuff.
It's always very stressful because you're on a time that to spew it out and.
Right, especially if you did it in a dark room or under a red light, you would have more time to do it.
Oh, I do. The water is big.
Epoxy is really useful because basically what happens is when you make this epoxide, that epoxide then goes through this ring opening reaction Where if you use water, you just wind up making a diol. But if you use another larger molecule, you wind up basically turning that entire thing gets turned into one big molecule. So it's incredibly strong and stable, and it keeps its shape so well because it's this ring opening reaction.
Awesome. That was actually really like 3D model. Like I literally cut the things the little tiny for hours to like it's like yeah.
This is for high school class.
And the school was like, can we keep this? Will you donate this? I said, it's in 6 class. But it took me hours to make and like I like the epoxy because I like it turns slow and fast so like piece here and then I had no time to like maneuver it when it was like partially.
Yeah, it had a good thing. They call it working.
Oh my god, I painted little green soldiers by hand. She did that. It was hours in the background. Like, and we lost half of them in the rocks because cutting rocks up on a stable saw, half of them still flying.
Right. Yeah. All right. Let's look at this one. Then we'll take our break. So once we have an epoxide, the next step is pretty much always we're going to break that cyclic ether open because it's not stable. So an acid catalyzed ring opening, we know what acid catalyzed means, and ring opening is exactly what it sounds like. So when you break a ring,
Thank you. This piece. Oh, that's
so
true.
it is today. Huh.
I don't need that. Oh. Continue.
So first step, proton transfer. It's acid catalyzed, so your first step should be proton transfer. Protonate the epoxy oxygen, which then makes it even less stable. And then we just have an SN2 reaction. It's just that our leaving group is still attached to the same molecule. Right? Because this is exactly an SN2. We've got a nucleophile coming in, acting from the opposite side of our leaving group. It's just that our leaving group doesn't go far because it's attached to the adjacent carbon still. And then we wind up with this intermediate where we've got oxygen positive charge again, another quick proton transfer. And we wind up making a diol.
Which is yeah.
So OL means alcohol, right? So a diol, it just means you have two alcohols. And a diol can be any molecule that has two OH groups is technically a diol. In this case, because they're on adjacent carbons, I think it's called a vicinal diol, which I actually don't know where that word comes from, but I'm willing to bet it comes from the same Latin root as the word vicinity.
Okay.
A vicinal diol just means that it's a diol where both alcohols are in the same vicinity.
Oh, well, it's alcohol. No, OH.
Here's good trivia for you. There are only two letters that are not used on the periodic table in any of the atomic symbols. You know what they are?
One is R, right?
No?
No? But
R doesn't get used just by itself, but there's RA,
oh,
RN. W is on there, tungsten.
B.
Vanadium. You're on the right track, but go with the more, even weirder letters. Show up even less. We know Z is on there for zirconium, Y is on there for yttrium and ytterbium. Q and J.
Okay.
Q and J don't show up in any atomic symbols. It used to just be J because until they added those last few,
Yeah.
it was un quadium.
They have those space eggs. The one here are people that would get nice with so like 4.
It's been since I've been teaching, I want to say it was like 2015, so it's been about 10 years. But people don't update their periodic tables very often.
Right. Well, then advice for like it's hard.
Yeah.
So that was probably. But I remember something like that.
It was 113, 114, 117, and 118 all got added at the same time in the same year. They, if I'm remembering correctly, it might be 114 and 115. Hang on. It was 113, 115, 117, and 118 all got added. They already knew livermorium, they'd already discovered, and fluorobium they'd already discovered. They hadn't found nihonium, moscovium, tennessine, or obenes.
I just remember it age like it was like hanging out.
Yeah. I mean, it doesn't really matter because how often are you going to use nihonium considering it's got a half-life measured in seconds? Right. But that is the other good one. The other good trivia of the periodic table. That's the only one named after and discovered in Asia. Nihonium. Nihon is it's my Japanese pronunciation is not that good, but that's the old name in Japanese for Japan. It's Nippon. And Nihon means from Japan. Tennessee was discovered in Oak Ridge, Tennessee, and Moscovium was discovered in Moscow. And Ogane, no, it's the name of a person.
Oh.
His research group found like 4 other ones, and then he died, and then his research group found 118, so they named it after him after he died. There's a few of them on there that are named after Seaborgium. Where's Seaborgium? 106. Glenn Seaborg worked at Lawrence Livermore Labs for his whole career, basically, and he found like 4 or 5 of these other really weird ones down here, like the Berkeley California ones. And he actually retired to Incline Village. So I actually had a periodic table signed by Glenn Seaborg. They got wrong. I lost it and moved somewhere. He's dead now too, so maybe I'll find it one day. But yeah, he was around up here for a bit. All right, let's take a break. Let's come back at 10 after, and we're gonna do we have 2 more mechanisms to do today.
Okay. And this was, what was this called?
This was, we made this is one. So the overall reaction, we call this a dihydroxylation because we added 2 hydroxide groups. So you call it dihydroxylation, you can call it epoxide, call it ring opening, call it diol formation.
Like back here, the overall ones we might have been sending to like the 2. I don't like this chart, it's just, we'll just like figure out a way to like.
So our last slide today is this that has a little bit of everything. So we'll go through all of them, and I think we have this one too, where we can fill in those variables. So we'll do some practice with that when we come back.
The arrangement. It's, you know, like.
Yeah, go through the important properties.
Wow, and adds like. They have, like, puts the headers on the sides on it, and hold it out. Order.
Yeah, we'll work on that.
What time are we have?
10 after. Going on, Brad?
Break time?
Break time.
Cool, because I wanted to show you a video.
Awesome. Let's see it.
All right.
It's about right.
Yeah. This had me dying. Just the humanoid running, wearing
with the baggy clothes.
It broke my brain.
It's yeah, robots are getting pretty good at doing weird stuff like that. It's definitely a little uncanny valley.
Yeah. Good time. How you doing?
All right, all right. How about you?
Doing okay.
Yeah, good.
It's almost that time.
It is. Wait, pitchers and catchers report in 2 weeks?
Yeah. It's about that time.
All right. And you know what? The Giants actually made some moves in the offseason. I mean, not big ones, but they signed a couple people. And
Yeah.
the Padres wind up doing anything?
The only thing they've done is, well, Mike Schill retired, or
Mhm.
manager. Get a new one, Craig Stanton. He's a former player. A little nervous, you know how it is sometimes.
Yeah.
Former players don't always, it doesn't always translate well to the
And
next.
and new managers always, if they've never been a manager before, you have no idea what.
Exactly.
Yeah.
So I'm a little nervous at the same time. It's like baseball a long time.
Yeah.
Hopefully it'll go well. We'll see.
You should look at John Boy. He's a YouTuber who does like baseball breakdowns. That's with an M. And
John, okay.
John Boy.
Okay.
He so he's got this whole like media empire that's taken off. It's not just him anymore, but he has a proposal for realignment and restructuring the playoffs that I'm really excited about. If they take like any pieces of it, because one of the biggest things is like if you're leading your division going into the All-Star break, you're in the playoffs. So if you win the first half, you're in the playoffs. You win the second half, you're in the playoffs. If you win the whole thing, you're definitely in the playoffs. But you only have to be like, so that accounts for like, shoot, we had a terrible May because we lost our ace for 3 months. And now it's time to, because then you're not like, I hate baseball seasons where at the end of May, you're like, well, my team's done. And that happens too much.
Yeah.
But when you still have that hope of, okay, well, but what about after the All-Star break? Now we can come back. We got 3 people back over the All-Star break.
Like 2 seasons essentially.
Yeah.
Yeah.
And then your overall seeding in the playoffs is based on your overall record. So there's still incentive not to tank the first half to win the second. But at the same time, you can still make the playoffs. If you watch his video, he's got some other good ideas in there too. Like National League only takes days off on Wednesdays. Every Wednesday, the National League gets a day off.
I think.
So that every 6 days a week, you know your team's playing.
I do.
Stuff like that would take a little getting used to, but it'd be kind of nice. It's kind of like football. Like, I don't know. Like football's gone the opposite direction. Now people are playing so many different days. I have no idea what's going on in ever, but it's it was a rough season for my Niners. And
Shanahan deserves coach of the year.
he did great. I always have the same problem with him, which is that he can't win the big games when he's so complicated. His schemes are that if you only have a week to prep for him, nobody can keep up with him. But you give another team 2 weeks to prep for him, he loses more often than not.
I hadn't even thought about that before. I mean,
that's why he got spanked by Seattle so bad this weekend, because they had 2 weeks.
Yes. I don't know. I can't completely chalk it up to anything.
There is free breakfast in the big bowl. Yeah, upstairs.
But team got so
nice. Oh yeah. No, for sure. They weren't going to the Super Bowl no matter what. It just sucks that we lost to the Seahawks of all people. Oh, I don't know if we can be friends anymore.
That boyfriend
No. My brother married into a Seahawks family and he is now a Seahawks fan.
I don't matter.
It's beside the, yes, they're good. I'll give you that. All right, we're gonna get back to it, Brad. Thanks for stopping in. See you later. Do you really?
I texted Nancy Shell. It's in her class? Yeah. I thought it was in Miss White's. Yeah. Well, Miss White got that.
That's
It's pretty. So like, these are like little army men that. And then those are the slides that she handmade. Well, they're all disguised, but they all have like chips over it. And they all says T. It was like a single brush, like a single. Yeah. It literally says. The guy is like against the nice guy, and then like, I read it's like, oh, it's like you can see all of the like hate from that, like they're not just like big like books.
Yeah.
They're not.
No, you put a lot of work into that for sure.
It,
Great.
what it's for, but I'm pretty sure I often see it. No, I think it was because I was in like this French like we read for both. And everyone else read it. So I went back to those class. They ran some of us, and we did not. So then I didn't know it was the removable. So they're like, tell us what you read. I don't know any shit. This is what we read.
Let's so when we make epoxides, we start with alkenes and we use these peroxide acids. They go through that convoluted 4 arrows at once transition state to do that, and then it's a really easy ring opening reaction. And when you do that, you always wind up, because that second step is an SN2, we're always going to make it trans style, where the two OHs are on opposite sides. So it's an anti-addition. If we want to put the two OHs on the same side, we want to go through syn dihydroxylation. And we do that using osmium, which osmium is right down here.
Okay.
So not really, doesn't really get used for much else other than heavy metal poisoning. Cause it. It's not super helpful. So the general mechanism, this is relevant to you too. The general mechanism for most heavy metal poisoning is if you get a metal that bonds more strongly than the metal that's supposed to be in that protein in your body.
Okay.
So like for instance, arsenic's not heavy metal poisoning, but the problem with arsenic, why it's deadly, is because basically arsenic can take the spot of phosphorus in ATP. And then you can't, and ATP works by breaking off one of those phosphates, right? When you do that, arsenic then sticks to the ATP too well, and you can't break it off. And so your cells just run out of ATP basically. Right, and so most.
Well, your muscles like stop working.
Yeah, it's definitely stable.
Oh gosh.
Yeah, and your brain cells run on glucose and ATP also. So your brain's pretty good at protecting itself from environmental toxins. They have that brain-blood barrier, but it's not perfect. And plus, if the rest of your body is shutting down because there's too much arsenic, your brain's going to die anyway. Osmium.
Yeah.
I don't know the mechanism by which osmium poisons you, but my guess is that it displaces iron in your blood, and then it's going to bond the oxygen differently and not deliver oxygen properly. It's going to be much bigger than the iron is. It's going to have similar oxidation states. That's my guess, but that's how most heavy metal poisoning works. Is you push out something that's supposed to be there and replace it with something that changes all the binding affinities.
And you're toast. Basically,
Alright, so in this case though, we're trying not to use osmium for heavy metal poisoning. We're trying to use osmium. It's osmium 8 oxide or OSO4. Because what happens is that osmium with a +8 charge, +8 oxidation state is not super stable that way. It gets more stable when it's closer to being neutral. When it's like in the +3 range. So what happens is you wind up with it reacting and you wind up making another cyclic group. This is a cyclic osmate ester, is what we call it. I'm not going to test you on that. But basically, the pi bond attaches to the oxygen. The oxygen osmium pi bond moves a lone pair over to the osmium, and then the other oxygen osmium pi bond moves over to the carbon to make this cyclic ester. And what's most significant about this, compared to what we were dealing with before, is both of these oxygens are sticking up now. So this is going to give us syn addition, because both of the oxygens are pointing towards us. So then the next step is just to reduce that osmium more. And basically, we're not going to show the mechanism for this part. Just like the demercuration step, we put it into mild reducing conditions. You bump the osmium off and you replace it with hydrogens. So our only difference, these are both dihydroxylations. In both cases, we're making that diol. The difference is just, are you making a trans diol or a cis diol?
and the difference is in oxygen or a.
Right. Or an epoxide. So the epoxide plus acid is going to be the trans diol. That osmium oxide gives you this 5-sided cycle, which then results in staying in the syn configuration.
Just sit here for a second.
Yep.
And only the trans has a plus EN.
The trans is going to be a plus EN. This one can be plus EN if there was something else attached here. Right, if the two directions around the ring were not the same. As it is, it's not plus EN because it's a meso compound. Remember that term? So meso is when it looks like that one should have an R versus an S, right? Because this direction around the ring is not the same as that direction, and it's got an OH and it's got a hydrogen. But because there's a mirror plane in the middle of the molecule, because the molecule is symmetrical, it means that this entire thing, if we took the mirror image of it, we get the same molecule back because it has that internal mirror. And we call molecules like that meso.
Would this be a meso-cis diol?
We just call it a cis diol, and it's not always going to be meso. It'll always be a cis diol. Because, so both syn refers to the addition being on the same direction. Cis refers to where the substituents are in the same direction. Syn leads to a cis diol. In anti-addition, leads to a trans diol. We're describing different things. We're using slightly different terms to describe different characteristics.
They just kind of sound.
Yeah. Yes. Well.
So it's a CIS. That's just this way on. Well, more like Latin major.
So as soon as we add something to one side here. Then our product is not meso. So we don't want to get used to thinking about meso as being the result of a
It's like,
mechanism. Yeah, it just means that one side of the molecule is mirror of the other side.
backward. I just want to be, I remember drawing those big things.
So in this case, and we would need to write plus En in this case. Because it's not gonna be the. It's gonna be a diastereomer, because not all of your stereocenters get flipped in this case. But we're getting in the weeds a little bit with that. So we have a lot of mechanisms now.
Yeah. Mm-hmm. So is this. It gives us. But what this
So in this case, you see the products.
you want to guess what happened in.
Yes. What do you have to do to go from this molecule to that one? So this Taylor goes along with you. This would be a good time to pay attention to your table and start adding things, because to go from this molecule to this, that's a hydration reaction, right? Is it Markov or anti?
The only hydration I have on here is wait. Well, it's on the waste steps. So,
So that makes it
not hard. Not hard.
anti-mark.
Which is, so that's a hydroboration.
Bingo. Followed by oxidation, right?
The CHM is still the only one at this point that's anti-mark.
We need an anti-Markov to get this one too.
Hydroboration.
Good.
Anti-mark hydro.
So is the hydroboration oxidation is the only anti-Markov hydration.
Right.
The other anti-Markov reaction we have was hydrobromination.
This is hydroboration. What's words forwards?
Hydroboration. Oxidation is the full name. The hydroboration is step 1 and oxidation is step 2.
And this one have rearrangement?
Nope.
But after all of the
Anti-Markov hydrobromination.
also it's the radical hydroboration.
Exactly. So we're going to be at just using HBr in the presence of a peroxide.
Your so if you feel like
So when we just learned the RO RCO380.
Mm-hmm.
Do you ever, seen like elbow bleeding on Rocco? Sort of made me think of which one? The RCO3H. And see, I can remember it, like it's Rocco. And no, Rocco. It's not. And then this one, this cleanup regulation.
No. Because otherwise it wouldn't be anti-mark talking about.
So anything anti-mark is not. We don't deposit it and remove it, it's gonna go to a more substitute. An anti-mark just. So.
So this one was a little bit, because it was free radical mechanism, it's a little bit weird. The first step was to add the bromine and make a free radical, and free radicals go on the more substituted, but because we added the bromine first. That's what makes the anti-mark problem, but don't pay attention to the free radicals too much at this point. That reaction gives us this.
This is two level.
Also known as a,
We have free radical.
no. Yes, the dial, that was rearranged.
No, it's not. Yeah.
It looks like we added the carbon or something because of that extra OH.
Or the dial scan. Which,
We're adding the same thing to both sides, so it's not. Just like with the hydrogenation, right?
and analytic approach. How.
And the halogenation.
And then how do you know if it's dial? What are your indicators?
It's got an OH here and an OH here.
It's di.
So
Well,
the-
just because like for some like the halogenation, you have BR2. Whereas the.
Oh, so what are so either of the ones previous slide would work for this because we don't care if it's sin or anything. We don't care about cis or trans in this case because,
So it could be used wrong and then be.
Yep. so RCO3H followed by,
Is it always gonna be that?
yes. So the R is just a generic placeholder. Usually we wind up using peroxyacetic acid. It's pretty commonly used, and there's one other one that is, I want to say it's solid at room temperature. So we use that, maybe peroxybenzoic acid.
Not spelled wrong. Yeah, well, because it's like imagine there's an O on R and C. Because there's an O at the end of Bravo too. And that's also like, oh, so it's O8, so it's the whole H style. Yeah, and then it's really well. Because we don't have the syrups, but it's a dihydroxylation.
The dihydroxylation is the name of the reaction. Dihydroxylation. So adding an OH group to something, an OH group, another word for it is hydroxyl group. It's like hydroxide. So dihydroxylation means you add two OHs. There's three more on this side, and two of them are easy. Which two are easy? Let's start with this one,
It's on the more substituted, which it has to be part.
right?
We have two options with the, we have four different options.
Except that we have to remember that we only want to add one film. Yep,
Good job.
there's HBr. That's also an acid catalyzed addition reaction. It's just that our second step is bromide adds, not water adds.
So technically, it could be different.
Could have, we didn't need to worry, so if we were worried about that, we wanted to stop it from rearranging. What's our other? As we don't really have a good way to do that with HBr.
But anything that's dark could be.
Anything that goes through a carbocation can rearrange.
This one could have been.
This one could have rearranged. This one, we have two choices for this. We have acid catalyzed hydration. That one could rearrange. It's acid catalyzed, so it's gonna go through carbocation intermediate. If we want to stop it from rearranging, what's our other Markovnikov hydration reaction? No, that was our, that's another name for just most addition reactions. The oxymercuration. But in this case, since we don't care about the rearranging, there's nothing for it to rearrange. Two, we could just use H3O plus to be acid catalyzed.
But it's oxymercuration, not.
That one will not rearrange. So if we're worried about rearranging, we'll use this one.
So oxymercuration has no rearrangement.
Correct.
So now this one has alcohol and the bromine.
We have a name for that.
Oh. Brominol. That was right.
Yes. A little hybrid. So this is the one that you didn't like that went through the three-sided bromine ring. So we just did.
You have that price.
Or we would have, this, we would use BR2 to make that intermediate, and then we just need to do it in the presence of water. The second step, because remember that with those.
So there's no 1, 2 on this one.
No. Because we want it to all be happening simultaneously, because the first step is gonna be. We make that bromonium ion. And then the second step, if it was dibromination, if it was just straight bromination, then we wind up with our bromine, our second bromine coming in here. And attaching. Actually, I drew it to the wrong one here.
This one has rearrangement.
Nope. But in this case, if we do this in the presence of water, the second step is going to be the water slowing pair comes in and pushes the bromine off of the more substituted carbonate. Sounding really enough?
Yeah, well, I looked at my notes. Yeah. There's just a lot to remember, like we learned a lot.
We have, there's a lot of volume, for sure.
Well, at least 6. At least 7, another 3.
Well, and these ones are gonna be simpler, and there's fewer of them. So this is basically, okay, well, if we can get to this, we can make it go through an elimination reaction, right?
Yeah. Technically.
Technically, it's been a minute. When we start doing synthesis, what we'll see is when we want to move functional groups around, we do a lot of do an addition reaction to put a bromine somewhere, then do an elimination to put a double bond there, and then we do another addition on the double bond. We just control the Markov converse to the anti and move it around where we want it.
Is there people that like their job is just
Synthetic chemists. That's what they do. They call it synthetic chemists. Their job is to figure out new synthesis pathways. So if the whole goal was to get here, and we were starting from there, your first step might be to do this, put a bromine on more substituted, because then we can do an elimination to get here.
well, so that is
And once we get here, now we can do a different dihydroxylation.
is there a mechanism for that one that if you want
This is the same as this one.
right is you mean like get one step to get to there? Yeah, right.
To go straight from here,
That. Yeah.
yes, it's only in last quarter,
It's
which is why Riley hesitated.
it can, but
So basically, to favor elimination, we want a strong base and heat. Because remember, heat favors elimination. Well, elimination is the opposite. Elimination, we're talking about Zaitsev versus Hoffman. Remember that?
get these guys out of it.
Those crazy Russians.
You have to worry about them on our winter. We gotta know.
Mostly Markov. But we're gonna keep coming back to how do we do synthesis? How do we get from point A to point B?
Is there two base? It's
If it's E1, you can have rearrangement. If it's E2, which with a strong base, you're more likely to see E2. Then it all happens in a concerted heat. Remember that? Maybe not.
I can't. I know that.
It's a Greek letter delta.
Oh, right.
So that one's review, but then once we do that, we make the more substituted alkene. Because we're gonna make the Zaitsev product.
That one first.
Let's do that one first. We could have made this one straight from our starting material. We didn't need to go through the intermediate steps to get there. Because what happens if you break a pi bond, you just replace it with H's. That's hydrogenation. Specifically catalytic.
Sometimes I forget this class is taking this class in gas.
Well, chemists do have the habit of, well, we're doing this thing and there's no word for it, so let's make a word up. Instead of trying to use words that we already have, they just make up a new word.
So this.
Which looks like. You need a hydrogen and you need a catalyst. It's mostly gonna be platinum.
I feel like we've done that once.
Yeah, we looked at it once and we said there's not much to do with the mechanism, so moving on. Nope, no rearrangement.
All of them, just keep costs. The pylon and replace it with the, like I said, I think these things come.
Yeah.
Before I put them in the state. It took off the pylon and replaced it with the price of this, that is still neutral, that's it.
And we would get the same product if we didn't have the dihydroxylation starting here.
Yeah.
So we didn't need to go through here first, but this was already crowded. That's my guess why they did that. If we want these cis dials, that's our new one.
Oh, yes,
The
that
one we
one.
just did the slide before this. We want to make dials. But we want them to be cis relative to each other, so we want the syn dihydroxylation.
Is that mark anti or neither?
Neither, because you're adding the same thing to both sides.
So. Dihydroxylation, it has to be formed. Sin or.
Exactly.
Or what?
Or anti.
So
This would be the syn.
how do you tell which is which just by looking at what's on the arrow? Like what if you.
So because if you have this calcium, it's always going to go syn. If you have
The other is.
the other one is anti. The other one is Paco.
Yay. Dihydroxylation.
What's the second step for the osmium is sulfite. I'm gonna go back in a second, but I just need to double check this. We need mild reducing conditions, so we use sulfite for it. Sodium sulfite in water. Yeah.
So something to there is that this, and this one would be great.
Nope.
The sin and the cis are the same mechanism. So they're not. The OHs are both going towards us in sin.
So in the sand addition, the OHs are cis relative to each other.
Yes. That's what I can say.
Right. The reason we don't call that cis addition is because the metal that's already there is now is trans to the other. So it just cis versus trans refers to where things are on a ring or on an alkene bond. And syn versus anti refers to the actual addition process.
Is that SOS?
Sorry.
OS? Not actually.
Yes, OS, or osmium tetraoxide, or osmium oxide.
This is.
No. Anti cannot rearrange either because that ring opening reaction is gonna go through, it's in SN2, she's inserted. So you don't have it here. Your first step is you maybe get oxide. And then, which can't rearrange because it happens all at once. And then the second step is you bring that water in from the opposite side as an SN2. And SN2 doesn't rearrange. I don't know why people think organics are.
So straightforward.
It's definitely one of those areas where any individual piece of it is straightforward enough to add back. But when you try and start layering things on top, there's a lot of things.
Yeah.
All right, we're not gonna add the last mechanism today. Because we only have 4 minutes left. So we'll start with that one on Thursday. That one's gonna be different. Because it's gonna be your first mechanism where we actually can move carbons.
It's a follow Pentecost. You gotta add a steam house, the kind of see where we're doing vegetables. And can dogs
So
there? Can we dogs?
just so you've seen it once. It's called, we won't go into the mechanism, it's called oxidative cleavage. Cleavage just means to break something into pieces, cut it
Yeah,
like a cleaver.
so then oxidation, we don't have to worry about rearrangement.
Correct.
Electrophilic,
So that one is the one that we put the acid catalyzed. That's another group.
so electrophilic and acid catalyzed separation are the same,
Yes,
so we do have to worry about it.
yes.
Hydrobromation,
Hydrobromination, yes.
about carbohydrates.
No.
And then our anti-mark, we never have to worry about rearrangement.
Correct.
And then our others are catalytic, hydrogenation,
No rearranging.
halogenation,
No rearranging.
anti-instant diagnostic drugs.
No rearranging. Dihydroxylation. No.
Okay,
Yeah.
so we could, so we have to worry about rearrangement.
Yeah.
It's like this type of oxidative gas gradient. I mean, that's what I would. Yeah, exactly.
We not within the side to say yes, no. All right, just so you've seen it once, since we have a minute left. This is also called ozonolysis, because we're gonna use ozone. O3 is called ozone.
Yeah.
Like the ozone layer. When you put ozone near an alkene, it breaks both of those. And you wind up breaking both of those bonds and replacing them with an oxygen.
Or do we just know that it's.
Yes. Treat, that we treat wastewater. Because bacteria have cell membranes, right? Cell membranes are made up of a bunch of fatty acid chains that are unsaturated, so they have a lot of this in them. If you expose bacteria to ozone, it kills it, breaks it up, and the cell breaks apart into pieces, dies. Because it does this through the entire cell membrane, so then the cell membrane just kind of falls apart.
If we have.
Because it's hard to do it at enough scale. Because it's a lot. We also have the ability to take CO2 and turn it into sugar by just planting plants, right? So why don't we just take the CO2 out of the sky if we have too much CO2? Because it's a lot of CO2 up there. It's a lot of ozone, and getting it up there would be the problem. But in theory, you could fly airplanes into the upper atmosphere and just release tanks of ozone. The practical aspect is what stops that.
Yeah.
All right, we'll end there. 1 o'clock, we have wet lab today. Talking about substitution and rates. Substitution kinetics is our lab today. So if you wanted to read up on that while you're eating your lunch, you certainly could. Oh, you have club, go do that. And then, yeah, Tuesdays are not a great day to have labs.
But.
But
You know, it is what it is.
when you